Back. This is Kid from KMS, and this is the second video on inequality MI. This is in the syllabus of IBHL Math. And last year, we saw in the first video that there was a first past paper question that's actually on this. If you count the specimens paper, it would be the second one. But I would say that most students would need more practice, and so in the last video, I posed these two questions as a practice. In this video, I'm gonna explain the solution. Okay, so if you actually try the question, you will actually see that the second one is easier. So we would tackle the second one first. Okay, so here we go. So let's copy the question first. So I want to show the statement 3 to the power of n is less than n factorial whenever n is bigger than 7, and of course n need to be integers, as always, for mathematical inductions questions. So that's our first question. Of course, we'll do the usual steps, so the easy steps, so like n equal to 1, for n equal to 1, the left-hand side is just 3. It's since that n equal to 1, because n need to be bigger or equal to 7, so our first case is actually 7. So it's 3 to the power of 7. Okay. Now you don't really need a calculator, but that would help. So in case this is a paper 1 question, it will be quite troublesome. But never mind, I press my calculator. I get 2,100 something. Okay, the right hand side. On the other hand, it's 7 factorial, which is, okay, where's my factorial button? See, it's 5,000 something. Okay, so the starting case is true. Okay, I will skip writing those stuff. Okay, so now we move on to the assumption step. So assume that the statement is true for some k. So that is, what do I have? I have 3 to the power of k less than k factorial for some k, where k is already bigger than 7. Okay, so k would have been bigger than 7. So k is bigger than 7. Okay, so for the next case, so for n equal to k plus 1, okay, what's going on? So we start from the left hand side. Sorry for the camera being a little bit shaky. My apparatus is not that professional. 3 to the power of k plus 1. So as usual, we want to create this 3 to the power of k. There should be some usual trick. And then we would use the assumption 3 to the power of k is here. 3 to the power of k is less than k factorial. So if we replace 3 to the power of k with something bigger, this is bigger, right? This is bigger than that. The overall thing would be bigger, right? Now then, you need to understand what we need at the end. What we need in the end is when k becomes k plus 1. So I want this to be, at the end, k plus 1 factorial. So I need to figure out why is this bigger. Our direction is bigger, okay? I want this to be bigger, bigger, bigger. Why is this bigger than 3 times k factorial? Okay? Now this is actually quite easy, okay? K plus 1 factorial is simply k plus 1 times k factorial. So all you need to do is figure out why is k plus 1 bigger than 3. Well, actually, that's totally true. If I change 3 to k plus 1, it will be bigger. Why? K is given to be bigger than 7, right? So k plus 1 is probably way larger than 3, since k is bigger than 7. K plus 1 is totally bigger than 3. So if I replace 3 to k plus 1, the thing would get bigger. So our direction is correct, our flow is correct. So at the end, I get the result that 3 to the power of k plus 1 is smaller than k plus 1 factorial, which is what I want. Okay, so that's it. That finished the question. Of course, you have to write the paragraph. That's your job, you know. Okay, so now we do the second question. Okay, if you try it, it's actually kind of tricky for this one. So I copy the question here. So it's 2 to the power of k plus 1 less than or equal to 2 to the power of n plus 1 less than or equal to 3 to the power of n plus 1. While n is just any positive integer. So this time our starting case n being 1. So let me show you again how to write the starting case. That's when this is 1, so it's 2 to the power of 2, which is 4. The right hand side is 3 to the power of 1 plus 1, so that's 3 plus 1 is 4. Okay, sorry, you can't see it in the camera. So no worry, 4 is indeed equal to 4, not less than, but in my side I have less than or equal to, so I have, I've allowed the case of equal, therefore this is still fine. Therefore, since 4 is less than or equal to 4, for the equal, this is true, this is a true statement. Therefore, for n equal to 1, this is true. Okay, this is actually the only case when you have an equal sign. Okay, whenever n is bigger, this guy would grow much bigger, much faster. So it would always be strictly larger than that from now on when n is greater than 1. Okay, but never mind, there's some technical problem when somebody create a question or write a question. They have to make sure that all the math are correct. Otherwise, you can complain, oh, the question have a problem. But for you, when you're doing the question, that equal sign doesn't really matter. Okay? So now we go to the assumption steps. So assume for some integer k, the statement is true. That is, 2 to the power of k plus 1 is less than or equal to 3 to the power of k plus 1 for some k which are positive integers. Okay, so assume this to be correct. Okay, then we go next. So when n is k plus 1, what happens is the left hand side becomes 2 to the power of k plus 1, right? So k plus 2. And as always, we break it to 2 times 2 to the power of k plus 1. So we take out one of the 2. And we kind of know that this would be less than this. So this is less than or equal to 2 times replacing it with something bigger, right? You replace with something bigger, the original thing gets smaller. It's smaller than a bigger stuff, right? So next we expand it. So 2 times 3 to the power of k plus 2. I hope you don't need me to tell you that you cannot multiply this 2 to 3 to 6 to the power of k. That's totally no good. Okay? Now, what do I want in the end, right? So I want all the direction to be like this. So every stuff to get bigger and bigger. And at the very end, I want to obtain this technical problem. We want 3 to the power of k plus 1 plus 1. Okay? Okay? So it seems that we need to create this 3 to the power of k plus 1 out of nowhere. Now, one tempting move to do, I will understand, is you change this 2 to just 3, right? Because if we do that, if we manage to do that, then we'll create a 3 to the power of k plus 1, right? 3 times 3 to the power of k is 3 to the power of k plus 1. And also, whenever we replace 2 to 3, the thing is supposed to get bigger, right? So it seems to be a very good move if we just change this 2 to 3. Stuff get bigger, the sign is correct. Now the problem is there's a plus 2 at the end. If now this is already this, I need to somehow make this plus 2 a 1. When 2 go to 1, it actually gets smaller. So now the direction will be wrong if I write this 2 to be 1. Okay? So that screws up everything. It makes this move no good because, I make the stuff a little bit too big when it's already bigger than the final answer. That's too bad. We cannot go backward. Okay? We cannot get really big and then get smaller again. That will screw up the direction. So keep in mind, when you do inequality MI, it's all about the direction. When the stuff needs to get bigger and bigger and bigger, you keep that flow until the end. So the end stuff is supposed to be the biggest. You cannot go the other way around. So we cannot reduce this 2 back to 1. So that's a problem. So now you need to figure another way to create 3 to the power of k plus 1. Okay? What's another way other than changing this 2 to 3? There's actually another way if you think about it. You have 2 copies here. You have 2 copies of 3 to the power of k. Okay? You kind of want 3 copies of 3 to the power of k, right? This is 3 to the power of k plus 1. What can we do is we can add another copy of 3 to the power of k, then 2 copies of it plus another copy with the 3 copies. So if we can somehow create another 3 to the power of k, we will be satisfied. So this is what I'm going to do. I'm going to all of a sudden add, okay, Okay, to make you understand this easier, I'm going to break this 2 to be 1 plus 1. Why do I do this? Because I do need a plus 1 at the end. So I want to reserve a plus 1. But then I replace this plus 1, the first plus 1, with 3 to the power of k. Okay? And then plus 1. I keep the plus 1. Now this is a good move. Why? Because when k is a positive integer, k is like 1 or 2 or 3 and so on and so forth, 3 to the power of k would always be bigger than 1. So I am replacing something smaller with something bigger. So my flow is correct, my direction is correct. So I can do this. Also, I managed to keep the plus 1, which I need at the end. Also, I created the third copy of 3 to the power of k. So that's it. That's actually how I do it. Okay, I'll break down this 2, and then replace one of the 1 with 3 to the power of k. This is, I admit, quite tricky. Okay? But that's the nature of inequality MI. You're allowed to do almost anything as long as the direction keeps going. Okay, so this is what you need to be careful of. You know, when you want the stuff to get bigger and bigger gradually, like this is the smaller one, this is the left hand side the smaller one, this is the bigger one. Your end result should have been the biggest one. So in the middle, if your stuff get too big, like we have the plus 2 there, and then I need to down the plus 2 to a plus 1, you know, that would be no good. So you need to be careful with that. Other than that, you can pretty much do everything. Okay? So that's why it's tricky, and I hope this video can help you to appreciate how to do inequality MI, because I believe in near future it will still coming out, because it seems that for the first time, not many students do it well for the inequality MI. So it seems that for IB, if for years somebody did, like a lot of students do a particular question badly, they will do it again. It seems to be like that. So I hope this would help, and also comment, subscribe, like, and also go to my Facebook page at Kid Math Studio to tell me what you want in the future. And it happens to be in Hong Kong, feel free to contact me in some way. Okay, so see you later.